everyone. Last week we talked about derivatives, we talked about rules of differentiation. Well, it's an extremely important topic, and we'll come back to it in the lectures. Maybe, yeah, let's do lectures. This week, for today and the next lecture, we are not going to talk about derivatives at all. So if you need some time to catch up with the material on derivatives, take this time right now. We'll talk about trigonometry. We'll talk about functions, sines and cosines. I want to ask first, how many of you have not seen sines and cosines at all before? Okay, so I will still go over sines and cosines briefly. And first of all, why sines and why cosines? So there are several motivations. The motivation that we will see in our course is, well, we'll see basically two. One coming from geometry, when you are given some problems, maybe a problem like this. So I given the angle, and you know its sides, say A, B, and C. And you know that it's right angle triangle. So you know there is a relationship between these sides. We talked about Pythagoras theorem. But then there are also angles. Say this angle, beta, and this angle alpha. Given the size of this triangle, how to find the length, the angles, alpha and beta? Or given the angle and one of the sides, how to find the other sides? So these are the questions from geometry. Or maybe the triangle is not even a right angle triangle, just a triangle. So it turns out that in all such problems in geometry, you need to use the same things over and over. Some measures of the angle, some functions of the angle, and they will be called sines and cosines. Another thing we'll see that sine and cosine are what are called periodic functions. They depend on their argument in a repeated way. So the way they depend on the argument in one interval is exactly the same as they will depend on the argument in some other interval, then some other interval, and so on and so on. They are very well suited for study of periodic processes, for example, oscillations, back and forth, transmission of signals in electronics, so all kinds of such things. That's another motivation. And finally, we'll see their solutions of some very little what are called differential equations. Once again, these differential equations themselves come from physics and engineering, and the mathematics of their solutions is once again trigonometry. So our topic is trigonometry. And the motivating problem would be exactly the problem that I outlined here. In a right angle triangle, so motivating problem. In the right angle triangle, with sides ABC and angles like 90 degrees, alpha and beta. How are sides and angles related? For example, given C and let's say alpha, find A and B. So that would be one of the questions which trigonometric functions will answer. For example, given the hypotenuse of a right angled triangle, given this long side C, how to find n in one of the angles, how to find the other sides. Alright, so let's start thinking about this question. Let me change this to this. Actually, so let me have this question. Given angle x inside C, find A and B. I just change the notation slightly. Now I have such a picture. That will be C. I'll call this angle x. This will be A, and this will be B. Let's start thinking about this question. So I'm given this length C. For example, I tell you this C is 5 meters. I give you this angle. For example, I tell you it's 74 degrees. I know also that this is 90 degrees. The question, what is this length and what is this length? Well, first of all, there is a simple geometric observation. I can take such a triangle with given length of side C, for example 5 meters, and scale it. It will not change the angles. So I can take this triangle and, for example, squeeze it or stretch it. It doesn't change the angle. What it does change is only the length of all the sides, but it changes them in the same proportion. So if I take a triangle and squeeze it by a factor of 5, all the lengths will become smaller by a factor of 5, and the angles will not change. I will have the same angles. So observation. We can stretch or squeeze a triangle without changing the angles. The more technically correct word will be neither stretch nor squeeze, it will be scale. So take this triangle and multiply all the lengths, all the proportions by a given number. And one convenient thing to do would be make this given length C equal to 1. So just measure everything in units of C, in units of this length. So we have a similar problem. After we scale this triangle by a factor of C, we get a triangle like this. This is going to be 1. This side is going to be A over C, which you still don't know. This is going to be B over C. And this angle is still going to be X. So after scaling by a factor of C. I still have a problem. I know this length is going to be 1. I know this angle x, think of something like 74 degrees. The question is still, what is this length and what is this length? I still don't know. Well, unfortunately, not going into new functions, not without introducing new functions of the angle, we cannot solve this problem. It's just not something like x squared, not something like x cubed minus 5. It's not something like one of the functions that we already know. So we invent a name for the answer. So instead of kind of solving this problem, we basically give up and say, okay, this problem is actually occurred, we'll have to give its answer a separate name. And that's exactly what we do. We do not know how to express this length in terms of x. So we give it a name. We call this length the cosine of x, and this length the sine of x. And that's exactly the definition of sine and cosine. So sine of x, here's the definition. In a triangle, right triangle with hypotenuse equal to 1 and the angle x, that's the length of the side opposite to the angle. Similarly, cosine is the length of the side in this triangle which is adjacent to the angle. Or, if we go back to this picture, this side length is A, B, and C, and the angle x, sine of x, well, we know what it is. If you scale this triangle by a factor of c, you'll get a triangle with side length is 1. Now we have a name for this length. It's going to be sine of x, and this is going to be cosine of x. So sine of x is going to be this thing, A over c. And cosine of x is going to be B over c. Sorry, that's the cosine, and that's the sine. Okay, so sine of this angle is the ratio of the length of the side opposite to this angle and the hypotenuse. Similarly, the cosine is the ratio of the adjacent side to the hypotenuse. This is a very disappointing answer, in a sense. We did not solve the question at all. We just say, well, whatever the answer is to this question, whatever this length is, we call it sine of x, and the other answer we call it cosine of x. It's not really doing any mathematics at all. We just say, all right, I have no idea how this length depends on x. I'll call it dependence by the name sine of x. It's kind of answer, but it's also not an answer at all. So the real question is, how do you find these things? How do you find sines and cosines of given angles? And the answer is, in general, it's complicated. We'll devote quite a lot of lecture time until maybe in the second semester we'll actually get to a point where we'll actually be able to compute sines and cosines of really complicated angles. In today's lecture, we'll just start with sines and cosines of really simple angles. So, our first task is sines and cosines of some arguably useful angles. Let's start with 45 degrees. One of the familiar angles. So let's compute sine of 45 degrees and cosine of 45 degrees. Well, in order to compute these sines and cosines, for now the only thing we know is the definition of sine and cosine. Sine and cosine are exactly the side lengths in a right angle triangle. where this angle is the argument of the sine. So let's see. 45 degrees is such an angle. If this and this side length is 1, this side is going to be cosine of 45 degrees, this is going to be sine of 45 degrees. First question. In this triangle, what is this angle? How large is it? What is it? 45 degrees. Right. So we know that the sum of all angles in triangle is exactly 180 degrees in any triangle. And here we already know that this is 90 degrees, this is 45 degrees, so what's left is another 45 degrees to complete it to a total of 180 degrees. So this angle and this angle are exactly the same. So here we have a triangle which has a symmetry. If you take this triangle and flip it side, so you take this triangle and flip it like this, you'll get exactly the same triangle. This angle will overlap with this one will overlap with this one. In particular, this length is exactly the same as this length. This side is exactly the same as this one. Once again, the argument, yeah.
Sorry, I'm kind of confused how a degree can also be a side length. So you have like cos 45 degrees is a side length. Is that just
so that's like this. It's cosine of an angle which is 45 degrees. It's not cosine of 45 as a number and then there's a number of degrees. So by definition, sine and cosine are the side lengths in triangle, right angle triangle with hypotenuse equal to 1. That's our definition of sines and cosines. We also, from this definition, concluded a different way to characterize sine and cosine is a ratio of two lengths. But, well, just in the very definition, the sine and cosine are side lengths in triangle. It's just we fix one of the sides to 1, and then we call the length of the other sides sine of angle and cosine of angle. So in this case, the angle is going to be 45 degrees. That's the angle. And the side lengths are sine of this angle and cosine of this angle. Alright, so once again, here we made an observation. This angle turns out to be exactly the same as that angle, which means that this triangle is symmetric about with respect to flipping it, which means that this side is exactly the same as this side. So let's give it a name. Let's say T, and this will be also T. So now we know that both sine of 45 degrees and cosine of 45 degrees are exactly the same thing, and we just called it T. How to find this T? I have a right angle triangle with the following sides. T, T, and 1. How do I find T? Yep.
t squared equals 1?
T squared equals 1. Why?
Because a squared plus, oh wait.
Okay, yeah.
Yeah.
So Pythagoras theorem.
Yeah.
If we know three sides in a right angle triangle, there is always a relation between them, called Pythagoras theorem. So here, Pythagoras theorem tells you that t squared plus another t squared is equal to 1 squared. This length squared plus this length squared is equal to this length squared. In other words, 2 times t squared is equal to 1. In other words, t squared is equal to 1/2. In other words, t is equal to square root of 1/2. That's the answer. Sine of 45 degrees and cosine of 45 degrees are equal to square root of 1/2. Usually we don't want to leave square roots in denominators, so usually we do some tricks to get rid of square roots of denominator. In this case, a simple trick would be to rewrite this as square root of 2/4, which is the same as square root of 2 divided by square root of 4, which is 2. But that's just, well, arithmetic. The important trick was like this. We wanted to compute sine and cosine of 45 degrees. We made a geometric observation, something about the symmetry of this triangle. Then we used Pythagoras theorem, a relationship between side lengths in a right angle triangle. And this allowed us to find these lengths. So here we have our first result. Sine of 45 degrees is square root of 2 over 2. Cosine of 45 degrees is square root of 2 over 2. Alright, that wasn't too hard. Any questions about this? Yeah? Question?
Yeah, how did we go from the square root of 1/2 to the square root of 2 before the square root of 2?
So from here to there.
Yeah.
From here to here, I just noticed that 1/2 is the same as 2/4. That's just 2/4. Cancel out the 2 in the numerator and denominator, you get that to 1/2. The reason I went from here to there, I wanted to have a square in the denominator. So that in the next step, I'll take the square root separately from the numerator and denominator. In denominator, I'll get a whole number. So square root of 4 will be 2. Does that make sense?
But isn't the square root of 2 not really, this doesn't really equal the square root of 1? Like I don't
So
understand.
here there are two identities. Here I'm using the fact that 1/2 is 2/4. Does that make sense?
Yes.
Yes, okay. So then the square root of 1/2 is the same as square root of 2/4. Then from here, I'm using the following fact. Square root of 2 over 4 is the same as square root of 2 divided by square root of 4. Does that make sense?
Yeah.
And finally, square root of 4 is 2. Okay?
Okay.
So this is an explanation for this step. And that's for this step. But once again, this is small detail. It's not about trigonometry really. It's about just a convenient way to write numbers. We just don't like having roots and denominators. But the important things is this, the geometry and Pythagoras theorem. Yeah.
I was wondering, so do you have to write it in that final form, or can you just write it as like dt squared or something like that?
So you can leave it in the form like square root of 1/2 or 1 over square root of 2.
Okay.
Just, it's not the standard way to write numbers. The standard way is to eliminate all the denominators in all the square roots, all the radicals and denominators. It's just, if everyone follows the same procedure, then it's easier to compare answers. Because if I give you the answer in the form square root of 1/2 and you give me the answer in the form of square root of 2 over 2, you will not know that we get the same answer. So there is a convention that we always eliminate square roots and denominators, and this way everyone gets to the same answer always. But you're right, mathematically it's exactly the same thing. Other questions? Okay, so inspired by this success, let's try to find some other sines and cosines. So new question. Find sines, let's say cosine of 30 degrees. Actually, let's make it 60 degrees. That would be simple. Alright, so cosine of 60 degrees. That's the new question. Well, again, we don't know at this point anything at all about sines and cosines except their definition. And the definition is construct a right angle triangle where this angle is the argument of the cosine, in this case 60 degrees. This length, the hypotenuse, is equal to 1, and this length is going to be cosine of 60 degrees. The length of the side adjacent to the angle. Alright, so here's a new geometrical problem. We have a triangle, this angle is 60 degrees, this angle is 90 degrees, this is 1. What is this side? Any ideas? Alright, let me give you a hint. The first step that we did here was find the other angle. Let's do the same here. What is the other angle? 30, yes. So here we have 60 degrees, 90 degrees, and what's left to complete the 180 is 30 degrees. Alright. In that picture, we made the observation that the other angle was exactly the same as the first angle. So we had a symmetry. Here, not quite. In fact, this angle is twice as large as that angle. So we don't have the symmetry here. But here's a beautiful trick. Let's create the symmetry artificially. Let's double this angle. Let me take this thing and create another angle of exactly 30 degrees. How can I do it? For example, just take this triangle and reflect it on this side. Flip it. What kind of triangle do I get now? Well, this length was 1. After flipping it, it becomes this side, which is also 1. Another thing, this angle is 60 degrees. This angle is 60 degrees. What about this angle? 60 degrees, because well, to get 180, you have to take 60 plus 60 plus another 60. So all three angles in this triangle are the same. It means that if you take this triangle and rotate it around the center of this triangle, so that this vertex becomes overlaps with this one, the triangle will overlap with itself. It means that all side lengths are exactly the same. So this length is exactly the same as this and exactly the same as this. Is also 1. Okay? So what is the cosine of 60 degrees? What is this length? 1/2, yes. So this side is twice the length of this side, because it consists of this side plus its mirror version. So if this is t, then this is another t, and 2 times t is equal to 1. So t is 1/2. Okay. So here it was even simpler. In a way, we didn't even need Pythagoras theorem. But we did need some non-obvious observation. The observation was that this angle was 1/2 of that angle, which was basically a coincidence which happens for this triangle and usually doesn't happen. And then we made some interesting argument about taking this triangle, flipping it, creating a triangle with all sides equal to each other, and then finding the length of this side, and then couple this side. Alright, what about sine of 60 degrees? How can you find that? Yeah? Pythagoras, exactly. So what is sine of 60 degrees? In exactly the same triangle, we have length, side length 1 here, 60 degrees here, 90 degrees here, cosine of 60 degrees here, which we now know is 1/2. This side length is going to be sine of 60 degrees. Well, if I know this side and this side, there is a way for me to find the other side. That's Pythagoras theorem. So Pythagoras theorem tells you that sine of 60 degrees squared plus cosine of 60 degrees squared is equal to 1 squared. In other words, sine of 60 degrees squared plus cosine of 60 degrees we just found was 1/2 is 1. Alright, so sine of 60 degrees squared is 3/4, which means sine of 60 degrees is square root of 3 divided by 2, by square root of 4, which is 2. So two things. One, we now know another two values for sine and cosine. Sine of 60 degrees and cosine of 60 degrees. Another thing, this relationship between sine and cosine is pretty general. We can apply the Pythagoras theorem in any right angle triangle, not necessarily a triangle with angle of 60 degrees. So, observation. Regardless of what the angle is, for any angle x, in this triangle, the side length is cosine of x, sine of x, and 1, we have the following relationship. Cosine of x squared plus sine of x squared is always equal to 1 squared, which is 1. So there is always a relationship between sine of an angle and its cosine. And the relationship is this. Sine squared plus cosine squared is equal to 1. In fact, we have to deal with squares of sines and squares of cosines so often that people agree on the convention. Here we have a notation for this which involves writing brackets. People agreed on the following convention. Instead of writing sine of an angle and then squared, people just write sine squared of an angle. That's just a notation. There isn't anything to explain here. It's just when you see such a thing, that's how it should be interpreted. It's sine of x, then square. Similarly, if you see such a notation, cosine squared of x, you should, what is being squared is the cosine. It's like this, it's cosine of x squared. So, our relationship is usually written in this way. Cosine squared plus sine squared is equal to 1. So let me summarize what we know about sines and cosines so far. Actually, let's get to the summary a bit later. Let's establish a couple more facts. So far we've talked about sines and cosines only for angles which can appear as angles in a triangle. For example, if you want to find out what is the sine of, I don't know, 70 degrees, what you have to do is as follows. Make, let's say, a horizontal line. From this horizontal line, measure the angle of 70 degrees. On this line, measure a segment of length 1. Draw a perpendicular to the horizontal line to create this right angle triangle. And this is going to be the cosine of 70 degrees. That's exactly the procedure that we did. Next question, does it make sense to ask what is the, let's say, cosine of 120 degrees? The answer is yes, it does make sense. And what you do is quite similar. You create a horizontal line like this. You measure 120 degrees. The problem with 120 degrees is it's more than 90. It's a little bit too much. So that would be 120 degrees. But then we'll proceed just as we did in previous case. On this line, we'll measure a segment of length 1. Draw a perpendicular. And measure these two lengths. This is going to be cosine of 120 degrees, and this length is going to be sine of 120 degrees. And it is natural to say that while sine of 120 degrees is still a positive number, the cosine is now negative. This length went to the left of the origin, to the left of the point where we started, not to the right, as it was for all angles from 0 to 90, but to the left. And this leads us to the following, I would say, extension of definition of sines and cosines. So far we only talked about sines and cosines for angles which were inside of the triangle. Now we'll talk about sines and cosines. So now sine x and cosine x, or x plot between 0 and 90 degrees. So here's the definition. You do the following. We start with the origin, like we started there. We take a horizontal line, like this. Then we want to find an angle x here, and measure segment of length 1 in this direction. How can we do it? Well, here's one way. Take a circle of length 1, of radius 1, and intersect this ray with this circle. So go in this direction until we hit the circle. This is going to be length 1. What is sine and cosine in this picture? Well, here's what they are. This length is sine of x. This length is cosine of x. In other words, the coordinates of this point, what is the horizontal coordinate of this point? Well, how much did you move in the horizontal direction from the origin? Cosine of x. How much did you move in the vertical direction from the origin? Sine of x. Why is this picture? First of all, this picture is exactly the same as the previous picture every time when the angle is between 0 and 90 degrees. Every time the angle is from 0 to 90 degrees, right here, we form a right angle triangle with hypotenuse equal to 1 and side length is sine of x and cosine of x. Exactly what we had before. But this picture gives you a sense of how to think about angles like 120 degrees. What is sine of 120 degrees? What is cosine of 120? Well, here's the answer. Do 150. So my next question is, what is sine of 150 degrees? What is cosine of 150 degrees? No, sorry. I did 120. So the question is, what is sine of 120 degrees and what is cosine of 120 degrees? Well, I'll go to this picture. I draw a unit circle on a system of coordinates like this. I will measure the angle of 120 degrees, which is like this. It's 90 degrees plus another 30. So it's something like this. This total angle is 120 degrees. And I go like this. I go from the horizontal direction, from the direction of the x-axis, to 120 degrees counterclockwise. Now, cosine and sine are just the x-coordinate and y-coordinate of this point. So the y-coordinate of this point is going to be sine of 120 degrees. The x-coordinate of this point is going to be cosine of 120 degrees. What are they? Well, that's actually simple, given what we already know. So any ideas about how to actually find these numbers? Yep.
Find an angle by line from 180.
So this angle is 120 degrees. if you go from here all the way to here, it's an angle of 180 degrees, an open angle. So the remaining part, this thing is what? 60 degrees. So right here, I have a right angle triangle with side length of 1, angle of 60 degrees. So what is this? What is this length? Okay, what is it? 1/2, yes. So we already established that in a right angle triangle with hypotenuse equal to 1 and this angle equal to 60 degrees, this is 1/2. So what should I say cosine of 120 degrees is? What is it? Negative 1/2. Right. So this length is equal to 1/2, but because the cosine is the x-coordinate and this point is to the left of the origin, not to the right, I'll put the minus sign. What about the sine of 120 degrees? Well, same logic. We already know what this length is. We established that it was square root of 3/2. And this still positive, still above the x-axis. Alright. Let's first questions about this. So the main new point here is the cosine of the angle being negative means just this point lies to the left of the origin, the point where you drop this perpendicular from the point of the circle. Let's establish a couple more angles, more sines and cosines, really simple ones. Sine of 90 degrees. What is this one? Okay, let's think about the picture. Draw a unit circle. Measure 90 degrees from this direction. That's right here. And measure, for sine, should I measure the x-coordinate or y-coordinate? Y. So the y-coordinate of this point is 1. Right. So sine of 90 degrees is 1. Cosine of 90 degrees is 0. That's the x-coordinate of this point. Similarly, sine of 0. Okay, so 0 means 0 angle. It means I start with this direction and don't go anywhere. So I'm talking now about this point. So what is sine of 0? So sine is the y-coordinate. What is it? 0. Right. Cosine of 0 would be the x-coordinate. What is it? 1. Right. Okay, so a short summary of what we know. So first of all, geometric problem. Sine of this angle is this ratio and cosine is this ratio. That's geometry. Another thing, we actually do know values of sine and cosines for some angles. So let me say x, sine x, and cosine x. What angles? 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees. Let me fill this table for you. 0, 1/2, square root of 2 over 2, square root of 3 over 2, 1, 1, square root of 3 over 2, square root of 2 over 2, 1 half, 0. So you should know these values. So you should just know these values basically by heart, or be able to derive them very, very fast using these pictures. And finally, we learned how to deal with sines and cosines of angles which are not between 0 and 90 degrees. So next time we'll start talking about the graphs of sines and cosines as functions. See you next time.